To understand why this invisible war is happening, you have to understand the fundamental flaw of digital video. It is impossibly heavy. At its core, a video is just an illusion. If your eyes see 30 images in a second, you don't see individual images. You rather see a continuous video. Take a standard Full HD image. It has 1920 pixels across and 1080 pixels down, roughly 2 million pixels in total. To create the colors you see, every single one of these 2 million pixels is a mixture of red, green and blue, the primary colors. Here is how a computer understands that. Let's zoom in to 1 pixel. The brightness of each of these 3 colors is assigned a number between 0 and 255. A 0 means that color is completely turned off, that is pure black. A 255 means it's dialed up to the maximum brightness. By varying the brightness of RGB pixels, you can get almost any color on the final pixel. Storing a number from 0 to 255 takes exactly 1 byte of digital space. So you need 1 byte for the red, 1 byte for the green and 1 byte for the blue. This means 3 bytes of data for the final pixel. Multiply that by 2 million pixels and you start to see the problem. Now, if you don't think this is bad, the math here is terrifying. Suddenly, just one single still frame of the video is taking up nearly 6 megabytes of space. If a video plays at 30 frames per second, with each frame being 5.9 megabytes, 1 second of video will be around 177 megabytes. 1 minute of video will be around 10.6 gigabytes. A 10-minute YouTube video will require about 106 gigabytes. Read this number again. It's not only expensive, it's downright impossible. Most consumer internet speeds top at around 1 Gbps, which is technically around 125 megabytes per second. If we tried to send raw video over the internet, telecom networks would instantly collapse. Your data cap would be gone in seconds. YouTube, Netflix, FaceTime, none of it would exist. The only way forward was to shrink the file somehow. But how do you delete 99% of the data from a video? More importantly, how do you delete 99% of the data from the video and still keep it sharp, keep it crisp, and keep it indistinguishable to the human eye? The answer to this question came in 1972 from a brilliant researcher from Bangalore, Nasir Ahmed. While working in US, Nasir Ahmed was obsessing over a mathematical concept. He called his idea Discrete Cosine Transform, or DCT in short. He didn't know it then, but this idea of his was going to change the internet world and trigger a war of patents, royalties, and billion-dollar lawsuits. To understand Nasir Ahmed's genius, imagine a simple wave. This is a graph of a cosine wave. The cosine wave smoothly goes from 1 down to -1 and back to 1. Nasir Ahmed realized you could use this simple wave to draw a picture. If 1 is pure white and -1 is pure black, this smooth wave creates simple gradient fading from white to black, then back to white. Now let's speed the wave up. This is a cosine wave with double the frequency. It goes up and down twice as fast. Now the image it creates changes faster too, white to black to white to black to white. Here is where the magic happens. Watch what happens when you add these two waves together. You get a completely new complex wave. And this new wave creates a completely new complex image with different shades of grey blending together. This new image goes from pure white to 22% white to 50% white to 22% white to 100% white again. By simply adding two basic waves, you just generated an entirely new picture. In fact, you can take the whole library of these waves, from slow waves to fast waves to hyper fast waves. If you mix them together in just the right proportions, you can recreate any image in the world. The color variations that you see in this final image are due to the weightage of high frequency waves present. Nasir Ahmed understood a fundamental flaw in human biology. See, our eyes are great at seeing the bigger picture, the slow, the basic waves that define general shapes, brightness and colors in an image. But we are actually terrible at seeing tiny rapid changes in details, and what are they represented by? They are represented by high frequency or hyper fast waves. Even in this image that we got, adding equal proportions of cosine graph from frequencies 1 to 10, watch what happens if we make the contributions of frequency 9 and 10 to 0. This is the resulting image. Can you see the difference in these two images? They are very similar, but the second image has 20% less data. This is how a raw image where each pixel is basically 3 bytes is converted to a compressed image format like JPEG. Let me show you very practically what that means. What you see on the screen is the raw image. Now this raw image is around 21 MB in size. Now I'll show you the JPEG version of this image. Did you notice any difference? The JPEG version of this image is just 644 KB in size. That is, JPEG image just has 3% of the information that the raw image has. But the question is, did you notice any difference? Let me show you the raw image again. This is the raw image, 21 MB in size. This is the JPEG image, 644 KB in size. Now, if you were very careful in looking, then some of you would have recognized some changes. But for the majority of you, these two were absolutely identical images. Let me first shift back to the raw image. Now let me zoom in here. Watch carefully on the highlighted portion of this image. Right now, you're seeing the raw version of the image. Each of this small box represent 1 pixel. So what we've essentially selected is, we have selected 8 cross 8 pixel square, which is 64 pixels. Now watch what happens if I now select the JPEG image. Now can you see the difference? I'm sure every one of you can. But now if I zoom out from here, you again won't be able to see the difference. Let me zoom out slowly. See? This is the JPEG version of the image, which appears identical to the raw version. Now let me zoom in again and you will start to see the difference. This is the raw image. This is the JPEG image. This is the raw image. This is the JPEG image. Now watch again carefully. This is the raw image. The raw image, each pixel is basically what the camera captured. Now what the computer tries to do is, the computer tries to represent these 8 by 8 or 64 pixels by a combination of these 64 discrete cosine waves. And then the computer reduces coefficient of lot of these high frequency waves to 0 using a process called quantization. Now when this image is reconstructed back from all the remaining low frequency waves, JPEG is what it kind of looks like, and because we got rid of around 97% of the image, it is very much visible here. Now what it means in practicality is, for example, if you look at this square, right? So in this square, in the raw image, you have pixels of very different intensities, but as soon as you shift to JPEG version of the image, you have only one type of pixel. So the computer only has to store 1 pixel with 3 bytes of data, and then computer can simply say for the rest 63 pixels, repeat this data. In this way, it has eliminated majority of the data. And for pixels like these, where it cannot essentially replace every pixel with just one type of pixel, it at least tries to remove the number of unique pixels, and therefore it kind of replaces all the pixels with a lot less unique average pixels. And what you get in the end is essentially a similar looking image, but with just 3% of the information, and that is how you compressed a 20 MB image into just 64 KBs of data. If you think about it, Nasir Ahmed invented the ultimate optical illusion. He figured out how to delete the data that our brains were already ignoring. To shrink a full moving video, computer engineers added a second equally clever trick. This is a video of basketball moving across black screen. So instead of storing each frame, you can only store the first image and only store the pixels that are actually moving on the screen. That is the pixels of the basketball. Therefore, the video is further compressed, this time without any quality loss. Now if you combine Nasir Ahmed's Discrete Cosine Transform and this interframe compression and you package it into a piece of software, it is called a codec. The video needs to be encoded to compress it, transfer it over internet, and then decode it back to be played on your TV. Encoded, decoded, hence the word codec. And this is where the story stops being about the brilliant science and starts being about the billions of dollars. In early 2000s, almost like every major company agreed to use one universal codec to make internet video work. Now this was called H.264. In fact, even today, it is the most popular codec. If someone sends you a video over WhatsApp, it's H.264. My Sony camera's footage is H.264. Even iPhone records in H.264 codec. Quick fact here, by the way, when YouTube came out, they were using H.263, but then in 2008, they also shifted to H.264. Now, why was H.264 so popular? Well, first, it was a big leap from the H.263 codec. In H.263, if a file size was 2 GB, then in H.264, it was just 1 GB for the same quality. But there was one more important reason. H.264 wasn't free. It was actually built on patents owned by tech giants like Sony, Panasonic, Microsoft, and dozens of more companies. Then a company called MPEG-LA or MPEG-LA pooled all these patents. They established a highly predictable licensing framework. Any company could basically pay to MPEG-LA and then use their codec without the risk of being sued. This is very important if you're running a large-scale business, right? And for large platforms, they even capped the annual royalties at a mere $100,000 per year, which is essentially a pocket change for tech giants. This allowed platforms like YouTube and Netflix to flourish. I don't think at that stage anyone could have predicted how crazily fast the video industry would grow. By 2010, the world demanded higher resolution like 4K or 8K. Do you remember a full HD image contains 2 million pixels? A 4K image has 8 million pixels. Now, to process 4 times more data, there was basically a need for a better codec. Now, these companies came up with H.265, and boy, is it brilliant. A video encoded in H.265 was half the size of H.264 for the same exact quality. Now, while engineers and mathematicians had done a brilliant job at creating H.265, the CEOs and senior executives of companies behind this codec got greedy. They saw how much money they had left on the table when the H.264 was launched. So suddenly now there were 3 patent pools instead of 1, including MPEG-LA, HEVC, Advanced, Veloce Media. And then some companies chose to remain independent. Also, by this time they could see how OTTs were the future. So now their contract wanted a cut of the subscription revenue. Here you need to understand something. Remember, a codec encodes and decodes. So for example, if my iPhone records a video, it is encoding the video. When I play it back, it is decoding the video. Now, because the mathematical calculations behind this are so complicated and huge, the processor actually contains a specific hardware to speed up these encoding and decoding processes. So for example, this TV has a pretty weak processor. But again, with a weak processor, it also has a special chip that can decode H.264 and H.265 video codecs, and thus it can play 4K content quite easily even though it has a weak chip. Now, for building this special hardware, a licensing fees needs to be paid to all these companies. Every TV manufacturer, phone manufacturer, companies like Intel, AMD, which makes CPUs, or companies like Nvidia, which makes GPUs, they need to pay licensing fees for building the encoders and decoders right inside their chip. Not only that, these agreements are so complex that not just device manufacturers, operating systems like iOS, Android, Windows, they need to pay licensing fees to these companies for having the right to play H.264 or H.265 in their device. Not only that, if you're using Adobe Suite, Adobe needs to pay licensing fees too, which is kind of weird. So for my TV, for example, first the processor manufacturer pays, then the TV manufacturer pays, and then if I'm using Netflix and paying for Netflix subscription, I pay to Netflix and Netflix pays a part of this to these licensing companies. If you think about all of this, who is paying for all? I am, or you are, and that too 3 times. In Germany, Nokia leveraged its H.264 patents to secure court injunctions, successfully banning major tech companies like Asus and Acer from directly selling their PCs and laptops in the country. Asus and Acer don't even make the computers themselves. They assemble computers and laptops. Every manufacturer of the actual chips inside those computers have actually already paid their licensing fees if you think about it. And if this extortion was not enough, the $100,000 cap on H.264 was now suddenly raised to $4.5 million. And the tech companies, the hardware manufacturers, have no other option than to pay up. In 2015, an unprecedented event occurred. These trillion-dollar corporate rivals, including Google, Amazon, Netflix, Microsoft, Apple, and Mozilla, came together and formed an alliance. The Alliance for Open Media, or AO Media in short. They had just one mission: They wanted to bypass the greedy patent pools and build a next-generation high-quality video codec that was completely royalty-free. In 2018, they released their creation. It was called the AV1 codec. This AV1 codec is even better than H.265. AV1 offers 30% better compression efficiency. The tech giants loved this. They rapidly integrated AV1 into whatever internet they controlled. Netflix, for example, adopted it. It allowed them to deliver 4K streaming to users who were using unreliable 4G and 5G data on their phone. So basically, your Netflix will consume lesser data for the same quality if it is streaming in AV1 codec. YouTube aggressively deployed it, and today over 75% of the YouTube's catalog is encoded in AV1 codec. In fact, you can check it. You can go to any video, then right-click on the video and then click Stats for Nerds. Most probably, you will see codec AV1. For Instagram and Facebook, over 70% of their global videos are now powered by AV1 codec. AV1 is also adopted by hardware manufacturers like Apple, Samsung, Qualcomm. They have built dedicated encoders and decoders right into the chip for smooth AV1 playback. My TV here, for example, also supports AV1. Now, if your TV is a 2020 model or a newer model, then there's a good chance it also supports AV1 codec. But just as AV1 was heading for a total victory, these patent pool companies have struck back. Do you think this party would last? Obviously no. The patent pool administrators realized that a truly free open source codec would destroy their multi-billion-dollar business models. So they went to a war. In March 2019, a prominent European patent pool administrator named Siswell launched a massive legal action against AV1. They said the underlying math around compression is essentially the same. Hence, the open source codec AV1, even though it is free, even though it is open source, is infringing on their proprietary patents. Their strategy is very interesting. Their strategy is they're not directly suing Google, like who is one of the founding members of AV1 codec. They know Google has infinitely deep pockets and they will lose against Google. They are targeting companies like Snapchat, which are relatively much smaller if you compare it to Google, but because they're using AV1 codec for their videos, Siswell sued them. Now these tech giants which are behind AV1 kind of anticipated this. So for fighting this, tech giants have even created a legal defense fund to fight against such patent disputes. So Snapchat can basically use this legal fund to fight its own legal battle. But again, still a lot of these companies have just paid royalties to Siswell because it's easier, smoother, and a court battle, on the other hand, is a bigger risk. The risk of business shutdown is much, much greater. So now answer me this. When all of these companies are suing each other so aggressively, do you remember this VLC media player, this orange cone icon? This player gets away with playing literally any format and you don't pay for anything, neither VLC pays for anything. Well, there are two reasons for it and both are brilliant ones, at least one is. One, VLC is purposefully registered in France, where you can't just patent like simple computer programs and math. So H.264 and H.265 patents kind of don't apply to them. Second, they are a non-profit organization. They earn $0. So essentially, what can anyone gain by suing them? But here there is a bigger question for all of us. Is it even possible to create a royalty-free video codec from scratch? Because if you think about it, at the end, a video codec is just maths, just some equations that need to be solved for. So is it even possible to reinvent maths? Nasir Ahmed, the genius behind all of this, did not earn a single dollar from these billions of dollars of royalties that were paid out to these companies. He gave the world the key to digital videos for free, while everyone else was busy in collecting toll tax from it.